Okay, continuing on with our standards, let's do mass and time. The current unit of measurement for mass is the kilogram. And this is used to be the standard, used to be a cylinder in France. So I'm going to say this. This is, but it used to be a cylinder in France. In fact, there was an actual cylinder, about twice this size actually, if you're on a normal computer screen, that had a mass of 1 kilogram. And that cylinder was the standard for the kilogram. So if you ever wanted to know what the mass of a kilogram was, you had to have some knowledge of this cylinder. Now they made a bunch of copies and sent them around the world, but still you were limited to this artifact, and that's what they actually call it, is an artifact. The problem with this, well, it had lots of problems, that first, it wasn't accurate. So it wasn't really good for measuring objects of a really small mass or objects of a really large mass. It just wasn't accurate for those things. It also was not unchanging. In fact, the kilogram was losing or changing mass with time. Not really known why, but it's thought that, there were either molecules from the air were attaching themselves to the cylinder. They cleaned it periodically, but still it would change mass, or maybe the actual platinum iridium atoms would jump off of the cylinder in some way. It was changing mass very slightly. And then, of course, number 3, is it accessible and is not accessible? So this is not an ideal standard, which is why a year or two ago they changed the standard for the unit of mass, and it's now based on a constant called Planck's constant. You might have seen this maybe in high school physical science when you're talking about the energy of a photon. The energy of a photon is equal or is proportional to the frequency of that proton. In fact, we'll see this a little bit later. And this constant is called Planck's constant or Planck's constant. What they do actually is they use a balance. It looks like this, like the scales of justice, and they have a cylinder on one side that is a kilogram, and they measure it, and then they base it on the other side. That cylinder is converted into an electrical current and then further described in terms of Planck's constant. So what you need to know about this is, one, that the standard used to be this cylinder in France, an artifact, and that now it is based on a physical constant, Planck's constant. And then it actually began with an actual balance, and they put a kilogram, probably the former kilogram, the artifact that they had, and then they convert that mass into a measurement based on Planck's constant. That shouldn't be really surprising. Actually, every time that you stand on a bathroom scale, really what you're doing is that you're putting all of your weight into, say, a spring that is underneath the scale, and it measures how much it compresses, and then that converts that into a weight. It's calibrated in a certain way to give you a weight. And this is a similar thing, except now instead of a spring, where we have an electrical circuit, and that electrical circuit is calibrated by Planck's constant. So the length is based on the speed of light, the mass is based on Planck's constant, and now time, we'll also see, is based on a physical constant. The current unit of measurement for time is the second. The standard used to be based on the fraction of a solar day many years ago. And of course, that's not accurate. It is not it's not unchanging, that a solar day can change with time. And then also, it's accessible to everyone, but it's just not a very useful standard. But now we define a second based on the period of an oscillating cesium atom. In a cesium atom, the electron oscillates back and forth at a very regular rate and a very well-known rate. So this is both, or it is accurate, it's very, very accurate, it is unchanging as far as we know, and 3, it is accessible to everyone. So now we have all 3 of our standards for measurements for length, mass, and time based on these physical standards, based on the speed of light for length, based on Planck's constant for mass, and also for the period of a oscillating cesium atom for time. And that is ideal what you want to have for standards of measurement.